Thank you. Welcome, everyone. My name is Pamela Wochner. I'm a research software engineer in the Research Engineering and Infrastructure team at TU Delft in the Netherlands. We are a fairly new team of 11 engineers that work on research projects across the computer science departments at TU Delft. And today I'm going to talk about the project I'm currently working on, Herb. So Herb's an open source Julia library for doing program synthesis. And it's named after Herb Simon, who's considered the founding father of program synthesis. So what is program synthesis? So most of you write computer programs, and sometimes that can be a very tedious and frustrating experience. So wouldn't it be great if you could just give a few examples of what you want? Some magic happens, and what you are presented in the end is a correct and executable program that does what you want. And by enabling to generate computer programs from a very high-level description, you can make programming accessible to a much wider audience. So hearing all of this so far, some of you might wonder, well, isn't that what my favorite large language model is doing? And to make it short, the answer is no. The type of program synthesis I'm talking about today is absolutely not what happens when you ask a large language model to write code for you, and I hope in the rest of the talk this becomes a bit clearer. So some of you might have encountered program synthesis before, maybe without even realizing it. So in the example at the top left, we see an Excel spreadsheet. And Excel has a functionality called flash fill. So here we want to extract the name of a person from their email address. And all you have to do is to give a few examples to Excel. Then you drag down this little black dot at the bottom right corner of the cell. And just like magic, all the other cells are being filled. And what's going on there is program synthesis. So to do that, we need a few ingredients. So first of all, we need a bit description of the problem that we're trying to solve, a problem specification. And that's usually done by providing some input-output examples. And I really mean only a few examples. The second thing we need is a grammar. So if you're in a similar situation to me when I started the project, I don't have a computer science background, and I had no idea what a grammar is. So the grammar is a set of rules that defines the programming language. So how can we read this grammar notation here? On the left-hand side, you have a symbol. The S here stands for string, because we're looking at the string manipulation problem. And you can iteratively and recursively substitute the symbol with the things on the right-hand side. And by doing so, you can create longer and longer computer programs. So the grammar for program synthesis could be anything. It could be like the Julia grammar, the Python grammar, or it can be something really, really specific. So the third component we need is a way to find a computer program. So we can combine the rules of a grammar, and in doing so, we get a computer program. And a computer program is typically represented in the form of an abstract syntax tree, where each node of the tree corresponds to a rule in the grammar. So to search for a program, this has two aspects. First of all, we need a search space. And second of all, we need a way to search this space. So in our case, the search space is the space of all valid program, and the structure of that space is more or less defined by your grammar. And for the search, we need search algorithms that are able to handle this tree structure and who can effectively traverse a tree to find a program that transforms the input and the desired output. A few more things on the search. So I mentioned before you could use a grammar like the Julia grammar, but that has many, many rules, which means that your search space would be basically too big. So you need ways to kind of narrow down the search. And one way to do is by using domain-specific languages. So in the example here, we look at the string transformation problem. So in the grammar, we only need rules that are relevant for strings and string manipulation. So domain-specific languages are also a way, not only a way how you can narrow down the search space, but how you also can incorporate knowledge that you have about the problem that you're trying to solve. A second way to narrow down the search is by introducing constraints. A constraint could, for example, deal with symmetries. So we all know that addition is commutative. So if we already explored a program that's 5 plus 3, there's no need to also explore 3 plus 5. And the research effort in program synthesis mainly centers around like the search. That's where most of the research is focused on. So next, I want to talk about some examples and applications that are hopefully a bit more interesting than string transformation. So on the left, you see this kind of collection of colorful 3D models of all sorts of objects. And most products start as a 3D model that's saved in a CAD file. And this file contains the product specifications. And usually how a model is created is by assembling various basic geometric forms into one single object. And at the end, you just save the model in a file. But what you really lose is the knowledge about all the steps a designer took to create the model in the first place. Now, program synthesis can do the reverse. It can take the final model and disassemble it into the basic shapes, into individual basic shapes that you can then edit separately. Another example is task and motion planning for robots, for example, in a scenario where a robot is supposed to navigate a kitchen and load the dishwasher. So, for example, some rules in the grammar there could be like pick up an object, move to the left, move to the right. And the last application I want to mention is polymer design. So polymers are widely studied materials whose like applications and properties depend on the molecular structure. Now, if you have a like symbolic graph representation of a polymer and a set of production rules, you can use program synthesis to explore and discover new polymers. So hopefully now we have a rough idea of what program synthesis is and what it's used for. The question is now, why Herb? Why this Julia library? And so to put it mildly, the field of program synthesis is a mess. It's been around since the 60s, so it's one of the more classic fields of AI, but every research group is doing their own thing. Existing methods are hard or impossible to run or proprietary, like the Microsoft Flashfill example. And benchmarks are often written in obscure language, so not very human readable, and also either impossible or hard to run. So researchers have basically no way to compare their own methods to existing methods or to reproduce somebody else's results. So we made the offer to like implement a framework that's mainly aimed at researchers in the field that allows them to run an existing synthesizer on their own problem or implement their own synthesizer and run it on existing problems and benchmarks. So Herb provides a way to specify a problem. We provide the building blocks to implement or re-implement program synthesizers. And it also comes with a number of already implemented and ready-to-use synthesizers and benchmarks. Okay, so sounds cool. How does it look like? So I have a code sample on the right. So it's like basically the same string transformation example from before. So we import the different Herb modules we need. We define a grammar. We specify the problem in form of input-output examples. We add a constraint, remember, to narrow down the search space. Then we need an iterator that's really central to the search, because the iterator gives you a way to traverse the search space. And then we have this function that brings it all together and synthesizes a program. So, and thanks to the utilities that Herb provides and the search functionalities, all of this fits onto one slide and in hopefully a way that you can more or less follow what this code snippet is doing. And believe me, this is a big progress in the field that this is possible. Usually code is like really, really, really long. So where are we now at the moment? So what's already quite advanced? We have efficient representations and enumerations for programs. We have a working constraint system, and we provide a lot of building blocks for people to implement their own synthesizers. What we still have to do more of is to provide implementations for existing synthesizers, add more benchmarks and problems other people can use to run their methods on. And also, of course, in the future is to find smart ways to integrate large language models, which are not just like wrappers around calling an LLM and let it write some code. So, and in the last slide, I just want to kind of show you the people or the core team behind Herb. The project is led by Sebastian, who's an assistant professor in the algorithmics group at TU Delft, and the PhD student he supervises. I'm in the team as a research software engineer. And there's also lots and lots of bachelor and master students that contribute to Herb. And I really want to highlight this part of the project because I think it's quite cool how much effort we make to like give students the opportunity that the work they do for their student projects or their thesis can actually contribute to a research library. So if you want to check out Herb, if you're interested, if you want to contribute, you can follow the QR code or get in touch. There's some tutorials. The examples in the tutorials are not quite as exciting. They're mainly on integer arithmetic. The reason for that is simply they're easy to understand. So that's my talk. Thank you. And I'm happy to answer questions.
Thanks very much, Pamela. So let's get Canopy up. So we have a couple of questions here. So what's the biggest or more complex program you've generated with Herb?
That's a question. I'm not sure if I can answer that. Probably the most ambitious we are working on is the abstract reasoning corpus. So that's like kind of a really big, famous benchmark. That's kind of quite hard to solve. So that's one that we're trying to solve. I don't think anybody has solved it properly yet. Usually all approaches do really badly on it. That's something we also want to try. The applications like the researchers focus on are more in like the biology, chemistry field at the moment. So it's really how to make something like this accessible for people who usually don't program.
Thank you. And final question, are synthesizers dependent upon the grammar of the language they synthesize, or are they independent such that any synthesizer can generate programs for any grammar?
I mean, I'm not sure if I understand the question. You provide the grammar, and the grammar is used to make the abstract syntax tree, and all the search happens on the abstract syntax tree. So they just work on like kind of the index of the rule in the grammar. So that doesn't matter what programming language it is. So all the search and so on, or even the evaluation, all works on the abstract syntax tree. And in the end, you just have a functionality that takes the abstract syntax tree and translates it back into a Julia code that you can actually execute. But you could, of course, also do this with, you can convert it back to Python or some other programming language.
Brilliant. Thank you, Pamela.